Welcome to this video on ad hoc circuit analysis, and in this video we're going to show doing ad hoc circuit analysis on a problem where we have a dependent source, and this particular problem is biasing of a bipolar junction transistor. So on the screen I've drawn two circuits. One is a circuit that shows a transistor, and the other is the circuit that you use to compute biasing for this transistor. Now, if you're interested in just the circuit analysis, you can skip the next minute or two, but if you'd like to know why this is a problem that's somewhat useful, let me explain. This symbol here in the circle, this is a symbol for a bipolar junction transistor, and it's a nonlinear device. It makes all sorts of really useful things possible because it can act as an amplifier. One of the things you need to do with a bipolar transistor is get the current that's flowing through it in the proper range for it to be useful as an amplifier, and this is called biasing the transistor. One way to do the biasing is to use a linear model of the transistor, and that's what we have on the right hand side. And everything that I'm circling here in green, this is the model of the transistor. And this model is reasonably good if you are biasing your transistor in the middle of its linear operating region. So the idea is typically you want to find a voltage that gives you a desired current through the transistor. In our case, because we're using this as an example of circuit analysis with a dependent source, this diamond, that the current through it is 50 times I sub B, is the dependent source. And the idea is that we want to just solve this circuit. So I've arbitrarily set the source voltage to be 1.7 volts, and basically what we want to find is what the output voltage is here. Now, one thing that I need to explain before we actually start working the circuit, you may or may not have seen this before. This plus 5 volts up here at the top, in fact, let me do this in a color that represents power. This plus 5 volts at the top means that between the plus 5 volts and the ground, which is represented by this symbol, there is a 5 volt voltage source. We oftentimes don't actually show the 5 volt voltage source because it's easier not to. It's cleaner. But what this means is that between this point that I've labeled plus 5 volts and the point that's labeled ground, there's a 5 volt source. So to make this explicit in our computation for biasing, I'll actually add the 5 volt source here to make sure that it's clear. Okay, so with that introduction, let's go ahead and figure out how to solve for the output voltage, this V out, in terms of the input voltage. So for this circuit, it's set up so that we can first solve for I sub B. Once we solve for I sub B, then we can plug in I sub B over here on the dependent source, and once we know what the current going through the source is, it's actually not very hard to find the voltage across the source. So our agenda today will be first to find I sub B, and then to use that to find the voltage across the current source. So if we look at the section of the circuit that defines I sub B, you can see that we have a single loop, and I can go around it like this. And so basically with a single loop circuit, we know from previous analysis, we can apply Kirchhoff's voltage law around the loop to find the current going through the loop. So if we start here at the resistor, we will have 10k ohms times I sub B, that's the voltage across the resistor, plus 0.7 volts, that's the voltage across this guy here, minus 1.7 volts. That's this 1.7 volt source, but we're going around the loop from minus to plus, and this all equals to 0. Okay, which I can then simplify to get 10 k ohms I sub b is equal to 1 volt. Solving this, I get I sub b is 1 volt divided by 10 k ohms. That's 1 over 10,000, which ends up being 0.1 milliamps. Okay, so what we know now is I sub b is 0.1 milliamps. In fact, let's write this up here. So we can erase our computations for I sub b to get now the output voltage. So since we know that I sub b is 0.1 milliamps, we can say that the current flowing through this current source, this dependent current source, it's 50 times I sub b. And so when we work that out, that gives us that the current through this source is 5 milliamps. And again, I got this 5 milliamps by multiplying I sub b times 50. Okay, and so if you look at this circuit, the 5 milliamps that flows out of the current source, the only place it can flow is around this loop. And that will be very helpful when we try to figure that out, what the voltage, the output voltage is. Now, some of you may ask the question, well, why can't it flow like this? Why can't it flow out and then somewhere into this part of the circuit? The answer is because the left half of the circuit is connected to the right half of the circuit only by this one connection here. And so if current is flowing out of the current source across this connection into this part of the circuit, there's no place for the current to flow back. And we know that current has to flow in a circuit. It can't just flow into one part of the circuit without coming back. So that's how we know that no current is going to flow from the dependent source back into this part of the circuit. It all has to flow around the loop that we have here that includes the 5 volt source and the 50 ohm resistor. So if all of the current is flowing in this loop, I can say that the voltage across this 500 ohm resistor is going to be 5 milliamps times 500 ohms, which, if I do my math correctly, this is 5 times 10 to the minus third times 5 times 10 squared, and this should give me then 2.5 volts. So I know that the voltage from here to here is 2.5 volts. Okay, so again I can apply KVL to figure out what the voltage across the source is. And I'm going to do that, but I'm going to do it in a way that is somewhat less formal than we've been doing in the past. I'm going to try to reason through this because this is actually a much easier way ultimately of doing it. This voltage source, this 5 volt source, sets the voltage from here to here equal to 5 volts. So there's a 5 volt drop from this point to this point. Now, I know that the voltage from this point to this point is 2.5 volts, which means that the voltage from this point to this point has to be 2.5 volts in order for the total drop from up here to all the way down here is 5 volts, which basically tells me then that V0 is 2.5 volts. Okay, so that pretty much is it. This turns out to be a pretty easy circuit to analyze because it's split into two different halves. First we analyze the left half to find out what our value for I sub b is, and then we plug that into our dependent source in the right half and use that then to find the output voltage that we want. So this concludes this video on using ad hoc circuit analysis techniques to solve a circuit with a dependent source. And hopefully you found it useful.